So let me start. Today we will have the last class this year, and next year we will make a break, and we will continue on the second week of the coming year, not on the first week. So the next class would be on 9th of January. Okay, so we are studying quantum field theory with and without H-bar. Quantum field theory with H-bar means functional integral. We already studied Mathai-Quillen integral in instantonic theories. Now we will go to Batalin-Vilkovitsky theory and BV integrals. Importance of this is because gauge theories that describe our world are a particular example of BV integral. However, BV integral plays a prominent role in mathematical physics. So I'll explain BV theory, and later I will come back to our models of quantum mechanics, like polynomials of degree n of z0 z1 and generalizations treated as gauge quantum mechanics, not written this way in books. So let me start. There are several inputs. Input one, concept of, okay, I'll call them DRAM, closed differential forms, and their direct image. If we have X over B, and here we have a fiber F, the direct image of omega is this, or integral of omega over a cycle in F. Surprisingly, this will turn into a BV integral. Point two.
Excuse me, Professor.
Yes?
What is omega?
Omega is a differential form on X. I will say more about it. I just outline.
And what is pi? Pi is, I suppose it's a projection.
Yes, thank you. Pi is projection. And here, proper thing is integral over fiber or cycle in the fiber. So in this sense, pi star depends on C. So it is this concept. The second concept is what's called odd Fourier transform. So the concept of odd Fourier transform is roughly speaking the following. I'll explain it later. It's a map between differential forms on X and polyvectors on X. Okay, here I write differential forms. So when we combine 1 and 2 together, we will get BV theory if we include Planck constant. So you may call it idea number 3. We will consider polyvector that equals e to the 1 over h. And here we have an object that is SBV. So SBV, so maybe this is idea number 3, would be polyvector on X taking values in formal power series in H. So when we put together ideas 1, 2, and 3, we will get BV theory. So let me explain them in the order. 1. Differential form omega on X may be considered as a function omega of X mu psi mu. Here I can say that X mu is even, psi mu is odd, or even. In the super case, parity of X mu equals parity of psi mu plus 1 moduli Z2. The RAM differential D is psi mu d over dx mu. Of course, d square equals to 0, and we say that d omega equals 0 means that omega is closed. Now, I would like to do the following. I will have a fiber F. Here is X, here is B. So I would like to decompose coordinates. At least I can do it locally. X mu could be decomposed into X fiber and also X base. Correspondingly, psi mu would be psi fiber mu, psi base mu. So let me do the following. Let me denote the index along the base with another letter like A. Correspondingly, the RAM is D fiber plus D base. Now, what would happen if I do the following? Take closed form omega on X. Take a cycle C in the fiber. And suppose I integrate omega like this. This would be function where it would be function on X base A, psi base A. That is a differential form on the base. And let me call this I. What can I say about I? I can say that D based applied to I equals D base applied to omega equals minus D fiber applied to omega. But then, since C is a cycle, it means that C is a cycle. This integral equals to 0. Okay, I can even mark this C with C, showing that this integral depends on the cycle. And this operation is called direct image. It takes closed forms on X to closed forms on base. And here I put C. So this operation depends on the cycle. Okay, so this is the first idea, first input. Now, I am coming to the second input. Okay, I will do it like this, so you can see the full logic. I am coming to the second topic. It's called Fourier transform or odd Fourier transform. So while first thing is pretty well known, second thing is not so known. It is known mostly in the case when X is purely bosonic. However, it has, as we will see, supergeneralization. So let me start with the classical construction 2A. We assume that X is equipped with non-vanishing top form omega naught. How can I write it? Rho of X psi 1 dot psi n. N is dimension of X. Let me remind that polyvector is a function on cotangent bundle to X shifted by 1 in parity. EF function of X, mu, and theta mu. These are coordinates in the fiber of T star of 1 over X, odd in the case when X is purely bosonic, it is even, so it's a standard case. Or, in general, parity of theta mu equals to parity of x mu plus 1. In classical geometry, there is an operation of contraction of polyvector and differential form. So P of x theta, it is called iota P of x theta applied to omega of x psi, defined as follows. We take P polyvector and we put d over d psi instead of theta. You may know it if P of x theta represents a vector field. That is, P is V mu of x theta mu then iota V mu of x theta mu is V mu d over d psi mu. And you can see it in the books. In most of the textbooks. Like in Cartan formula, LV, and the formula I or iota. Iota is the generalization to polyvectors. So why they are called polyvectors? Because P of x theta could be written as sum over k from 0 to n, P, I call it k, mu1, mu k of x, theta mu1, theta mu k. So they have k upper indices, so they are generalizations of the concept of the vector. Okay, so after I discussed polyvectors and the operation of internal contraction, I will write down thing that is a map between polyvectors and omega and differential form. It is P omega correspondence. Omega corresponding to P is iota of P applied to omega naught. So this is an isomorphism. In particular, I can also say inverted. And consider P that depends on omega. In particular, P corresponding to omega naught is 1. I can do the following. Let me call this transformation. Okay, I will write it in this way. So this I will call f minus 1. So f minus 1 takes p into omega. And there will be also transformation f that is inverse from omega to p. I can do the following thing. I can take the RAM operator and I can do the following. I will define Batalyan-Vilkovitsky operator. Define like this. So what is it doing? This operator takes polyvector into polyvector. So f minus 1 takes polyvectors to differential forms. So let us write it like this. So here we have polyvector. F minus 1 gives us differential forms. And F gives a polyvector. And here we are acting by D. It is instructive to compute delta BV. But before we compute it, let me remark that from definition, it is clear that delta BV squares to 0. really. So this gives identity map, and here I have d squared. Now, it is instructive to compute it. Let us, for simplicity, compute it in coordinates when rho of x equals 1. Claim in this case delta BV equals let me try to explain you why it goes like this. And the reason is that F is an odd version of Fourier transform. So it takes psi. So it takes d over d sorry, so it takes psi mu to d over d theta mu. And correspondingly, I'm sorry, misprint. So I need to explain this. Another way to write P going to omega is sorry, and here I put exponential maybe it's better to write it down as a standard Fourier transformation. It is in the case rho of x equals to 1, and let us try to understand it in this particular case. So what happens if p is equals to 1? Then in order to take this integral, I have to expand the exponent n times to take the integral, and I will get psi 1, psi n. Actually, there is factor n factorial from the exponential, and there are also n factorial ways to take thetas for Berezin integral. So n factorial cancels out. Now I want to see how I should modify this in the case where rho of x is not 1. I just have to put rho of x here. So why it is like Fourier transform? I call it odd Fourier transform because in standard Fourier transform, we integrate. Let me call it y. But this is a standard integral, while this is Berezin integral. So you may compare formula that is odd Fourier with the formula Fourier. So let us continue. In the standard Fourier transform, k f tilde k equals to 1 over I. Similarly, in the odd Fourier transform, psi times omega of x psi goes to, and here I have d theta 1, d theta n, Pauli vector. Sorry, I misprint. Okay, so that's for rho equals to 1, delta is this. Okay, now we will combine 1 and 2 together. So how are we going to do it? Step A. Let us go to supercase. And when we go to supercase, we do the following and rethink what is integral of differential form over the cycle in the fiber. We will do it like this. We will say that this equals to, locally, integral d psi. Okay, so let me do it first when I here have a fiber. If I have here d psi fiber mu, okay, let me put this index I, and let me take here integral over df, dxf in the fiber I. And here I have functions of psi fiber, x fiber, psi base, x base. And now I am going to do the following. I will try to apply odd Fourier transform. So how can I do it?
Sorry, Professor. I may misunderstand something. Here we integral in the fiber, but the coordinate x Is it in the body? In the
in the both. Okay. There is coordinates x in the fiber and in the base. I want to write it this way. So here we integrate only in the fiber.
Oh, I see. Oh, I see. Okay. Oh, I see. Thank you.
So I am going to rewrite it in terms of polyvector. So I will keep this integral. Sorry, of course, product over I. And it's proper to put this product inside the integral. I keep this alone. And here I see, what do I see here? I see here the odd Fourier transform for theta equals to 0. No theta here. So here I have I'm sorry for writing these integrals too much. Polyvector X fiber 0. And also here I have psi base A, X base A. So this is the result of this integration. And later I may perform odd Fourier transform on the base. That I am not going to do right now. I want to point the following. Important point. So here I have suppose that this is a fiber. And this is T star to the fiber. I integrate over this line. And this is Lagrangian submanifold in T star F in that's what happens. And I may think, because here, okay, I'll write it in green. Yes, please ask. It is non-trivial step.
Professor, you shift the parity of the cotangent
Yes.
fundament.
Yes. So it is a Lagrangian submanifold for what?
Does
For
it mean
symplectic form. That is d theta I dx I. So I put here fiber. And this is odd symplectic structure. Or BV, Batalin-Vilkovitsky symplectic structure.
and this omega is actually symmetric? Is that right?
Yes, omega is symmetric. Really, it's a good point. So it is a super world. And in the super world, the concept of symmetry under when you interchange things is a bit different. Of course, you're absolutely right. D theta and dx are symmetric, but the concept of Lagrangian submanifold holds. So let me consider some cycle here. So I am going to this formula that I call fiber integral. Not functional, fiber integral. And let me do the following. Let me consider a cycle in the fiber. Say x fiber 1 equals to 0. Okay? So if x fiber 1 equals to 0, how I am doing the integral? I am doing the integral over dx fiber 2 d psi fiber 2, etc., dx fiber n d psi fiber n. And here I put omega of X fiber, psi fiber, where I clearly, of course, X base, psi base, and in this omega, I clearly put X fiber equals to 0, X1 fiber, and also psi fiber 1 equals to 0. And now I would like to understand it in terms of the polyvector. So in order to get it in terms of polyvector, I can do the following. I can say that this is and here I put d psi fiber 1. Okay, here I put L dots. And here I want to have d psi fiber 1. To come back to the odd Fourier transform. However, I do the following. I'll take an extra integral over d theta 1. And here I would put, sorry, index goes down. And here I will take exponent of theta 1 psi fiber 1. And here is my omega. Evaluated when X fiber equals to 0. You may ask, where condition psi fiber 1 equals to 0 goes? This condition comes here. Taking the integral over theta 1 brings psi fiber 1 down. And I cannot have any psi 1 fiber from omega. So it is non-trivial step to replace this condition by an integral over theta. It is known the integral representation of the delta function in odd variables. So now I understand that I am making the integral over d theta 1 later. dx fiber n but I have the Fourier transformation. What Fourier transformation? And here I have Pauli vector that depends on theta 1. Oh, I started with x's. So let me start with x so that you would not misinterpret it. So here I have x fiber theta 1 okay, I will write it properly.
Excuse me, Professor.
0 x fiber 2 x fiber n. Sorry. I cannot draw properly. And while here I get theta 1 and the rest of thetas are zeros. 0, 0. And then I have x base, psi base. Yes, so now I am ready to answer questions.
So in the integral above, should you remove the restriction sign for omega because you already integrated over theta.
You see here is the restriction sign only for x. Here I have restriction sign for x. I already removed the red restriction, but I still have the green restriction. And in
Okay.
last integral, I put this green restriction here. So I don't want to rush. It is an important point, important conceptual point. And how can we draw it? We still can draw it. So here we have T star shifted by 1 of f. Here we have f. And here we are integrated like this. So it is xf1 equals to 0. Theta 1, of course, f unrestricted. And this is again Lagrangian submanifold. So previously Lagrangian submanifold was horizontal along the fiber. Now, at least in x1 coordinate, is vertical. So thinking this way, we are getting the following important condition. Generalizing, we say that integral over the cycle in P star goes into integral over Lagrangian submanifold. And this is called BV integral. So altogether, this goes into integral over the Lagrangian submanifold. In particular, if d omega equals to 0, and it is exactly the same that this equals to 0, then I will write it down explicitly. Delta BV on the base applied to such an integral and this is the theorem for direct image for BV integrals. And now the last ingredient that I promised to show. We will take P of the very special form. S of H is a polyvector with the values here. And we impose condition delta BV on polyvector equals to 0. So it is idea 3. It corresponds to, and it's interesting to compute. You may do the computation. So first, I take derivative on S. Okay, I'll do the computation here. Okay. And then I take derivative again. When I differentiate here, I get delta S. Sorry, I forgot 1 over H. Plus, I will have derivative when I differentiate here. And so I'll get ds over d theta mu, ds over dx mu, and actually there is a sign. So let me see if there is a sign, no sign in such description. Okay, and all this multiplies exponential 1 over h s over h. So in this way, I am getting, by multiplying by h squared, I am getting so-called quantum master equation. Together with quantum master equation, I have a classical master equation. Taking h equal to 0, we get classical master equation. Sometimes people write it in terms of bracket of S and S equals to 0, and this is called BV bracket. It is important since many concepts, I'll write it down, of mathematics have the form SS equals to 0. And quantum master equation is a uniform way to quantize them. We will discuss it next time.